Hello student. So in this video we'll study about bipartite and planar graph. So let's start bipartite graph. So bipartite graph is graph in which the vertex set is divided into two subsets. So if there are 5 vertex in the set of vertex set, we'll divide that into 3 or 2, 1 or 4, okay, in any two subsets. Like for example, in this graph we have 5 vertices. We have divided those 5 vertices in set of 3 subset, 3 vertices here and 2 vertices here, so that some vertices from this set are joined to some vertices of the other set. Okay, so such kind of graph is called bipartite graph. And one thing in a bipartite graph, if there are 2 vertices in set A, then those 2 vertices will not be joined together. Okay, so this is not a bipartite graph because here you can see the 2 vertices of the same set, same subset of the vertices are joined with each other. So this is not a bipartite graph. One vertex from set A can be joined to other vertex of set B, okay, but they cannot be joined with each other. Okay, so complete bipartite graph. A complete bipartite graph is that graph in which every vertex of A should be joined with every vertex of B. Okay, here the condition of every is not there. One vertex can be joined to 1 or 2. Okay, one vertex can be joined to 2 or just 1. One vertex can be joined to 2 or just 1. But in case of complete bipartite graph, if I have a vertex here, it should be joined to all the vertices of the second set. Okay, so every vertex here should be joined to all the vertices of the second set. So this is a complete bipartite graph. Complete bipartite graph is always denoted by Kmn, where m and n are number of vertices in A and B. So this is K32 because in this set, this vertex set, I have 3 vertices. In this vertex set, I have 2 vertices. So this is called K32. This is K33. You can see one vertex is joined to 3 other vertices. One vertex is joined to 3 other vertices. One vertex is joined to 3 other vertices. So this is complete bipartite graph. Next is planar graph. A graph is planar if it can be redrawn such that no edges intersect with each other. Okay, suppose if I have this graph, here you can see this edge is intersecting with this edge. But suppose if I remove this like this, okay, I can place this edge this side. It can be redrawn this side, right? So graph will look like this. So such kind of graph is planar graph because this graph, we have redrawn this graph into this graph. And in this graph no edge is intersecting with each other, so such kind of graph is called a planar graph. K5 is not planar. You can see this is K5. K5 is a complete graph having 5 vertices, and in a complete graph every vertex is joined with other vertex. So vertex A is joined with B, C, D, E. Vertex B is joined with A, E, C, D. Similarly, C is joined with all other vertices. Similarly, D is joined with all other vertices. Similarly, E is joined with all other vertices. Okay, so this is a complete graph having 5 vertices. This is not a planar graph. If suppose this vertex is cutting this edge and cutting this edge is cutting this edge and this edge here. This is also cutting this one and this one. So I can remove these 2 edges. Okay, so graph will look like this. I can put these edges here. I can put this edge here. So the graph will look like this. Okay, but what about this edge? This edge cannot be redrawn in any manner. It can't be redrawn like this. If we redraw it like this, it will cut here. If I redraw it like this, again it will cut here. So there's no way to redraw this graph so that the edges don't cut with each other. So that's why K5 is not planar. Next, faces. a plane graph partition the plane into several regions. Those regions are called faces. Okay, whenever we have a plane graph, it divide the whole plane into several regions. Those regions are called the faces. And the number of edges which form one particular face is called degree of the face. Okay, suppose I have this graph. Here you can see this is face 1, this is region 1, phase 1, this is region 2, phase 2, this is region 3, phase 3. Okay, so and what is the degree of the face? The number of edges which form this particular face is the degree. Like here you can see 1, 2, 3. 3 edges are forming this region, so degree of F1 is 3. What about F2? 1, 2, 3, 4. So degree of F2 is 4. F3, 1, 2, 3. So degree of F3 is 6. What about F4? This is an infinite face. How many edges are making this face? 1, 2, 3, 4, 5 and 6. So 6 edges are making this face. So degree of F4 is 6. Next, let's prove a very important formula called the Euler's formula. So the Euler formula states that the number of vertices plus the number of faces minus the number of edges is always equal to 2. Okay, we represent number of vertices, F represent number of faces and E represent number of edges. So in a planar graph, V plus F minus E equal to 2. Okay, so to prove this formula, we will use induction on the number of faces or number of regions determined by G. Okay, so if F is 1, if there is only one face, then that face will be an infinite face. If F is 1, this graph can form this kind of face. Okay, so in this graph you can see edges, number of edges is 1, number of vertices is 2. So E is 1 and V is 2. So what will be my V plus F minus E? V plus F minus E will be 2. 2 plus 1 minus 1, which is equal to 2. So result is true for F equal to 1. So if phase is 1, the Euler's formula holds. Now suppose the result is true for F if F equal to K. So if number of faces are K, then let us assume that V plus F minus E is equal to E. Okay, so for a graph having V vertices, E edges and K number of regions, we have V plus K minus E equal to 2. So we are assuming this result and we will prove for K plus 1 faces. Now let G be a graph having K plus 1 regions. Let this be the first region, second region, third region, fourth region, fifth region, so on, 7th, 8th, 9th and K plus 1 region. Okay, and let in this graph we have V vertices and we have E edges. Then we need to prove that V plus K plus 1, which is the number of faces, minus edges is equal to 2. Vertices plus faces minus edges equal to 2. We need to prove this. We have to prove this. Okay, now suppose if we remove one edge, suppose we remove this edge. If we remove this edge, the graph will look like this. Okay, so in this graph, how many edges are there? There are E minus 1 edges, because one edge is removed from here. Here the number of edges were E. So here the number of edges will be E minus 1. Vertices are same, no vertex is removed here. And how many faces will be there? One face is removed. Okay, 1, 2, 3 here, one face is removed. So faces will become K. Okay, so let this graph be G dash. So G dash has E minus 1 edges, V vertices and K regions, K faces. Okay, and by our induction hypothesis, by our assumptions, the Euler's formula hold for K regions. We have assumed this, that the Euler's formula hold for K regions. So according to that formula, number of vertices plus number of faces minus number of edges will be equal to 2. So V number of vertices plus K number of regions minus number of edges is equal to 2. So if I open this bracket, this will become V plus k minus 1 plus 1. V plus k minus e plus 1. Okay. So this will become V plus, if I combine k with plus 1, it will become V plus k minus e equal to 2. Okay. So this is what we have to prove. We need to prove this. We have proved this. So hence the Euler formula is proved. Next, let G equal to V comma E be a simple connected planar graph with more than one edge. Then the following inequality holds. 2e greater than or equal to 3r, and second inequality, e is less than or equal to 3v minus 6. E is the number of edges, r is the number of regions or faces, and v the number of vertices in the graph G. Okay. So let's prove the first inequality first. Since G has more than one edge, the graph G has, it's given that the graph G has more than one edge. So E is greater than 1, number of edges greater than 1. Okay, so let's assume this as equation 1. If G defines only one region, then R is equal to 1. If there is only one region in G, then R is equal to 1. So this implies 3R is equal to 3. Okay, if we multiply this equation both sides with 3, we get 3R equal to 3. Now from equation 1, E is greater than 1. From this equation we have E is greater than 1. If we multiply by 2 both sides, we get 2E greater than 2, and we know 2 is greater than 3. So 2 is greater than 3. So if we substitute equation 2 here, we get 2e greater than 3. Now if we substitute equation 2 here, we get 2e greater than 3r, because from equation 2 we have 3 is equal to 3r. So 2e greater than 3r. So if region is 1, then the first inequality holds. Okay. Now if region is greater than 1, if R is greater than 1, then let us define B be the total boundaries of regions. Okay. Total boundaries means if there are 5 regions, then we count the boundary of each region. Okay. And that total count is B. Okay. So if I have this graph, so if for this region I count the number of boundaries, there will be 1, 2, 3, 4. Okay. For this graph, if I count the number of boundaries, it will be 1, 2, 3. So 4 plus 3, 7. And then for the infinite phase, if I count the boundaries, 1, 2, 3, 4, 5. Okay, so 4 plus 3, 7 plus 5. They are 12 in number. So number of boundaries are 12. Okay. So each region is bounded by at least 3 boundaries. You can see here in this graph that one region will be always bounded by at least 3 boundaries. Okay, there will be at least 3 boundaries, and those 3 boundaries will make the region. If there are R regions, then B will be at least 3R, because one region is made by at least 3 boundaries. So if there are R regions, so number of boundaries will be at least 3R. So B is greater than or equal to 3R. For one region we should have 3. Okay, we should have at least 3. For 2 regions we should have at least 3 into 2. For 4 regions we should have 3 into 4. So for R regions we should have at least 3 into R. So number of boundaries are at least 3 into R. It can be greater than 3 or also greater. So it's greater than or equal to 3R. Okay. So we named it as equation 3. Also, each edge is counted twice in boundary, as you can see when I was counting here the boundary. So this edge was being counting twice, one for this region and one for this region. Similarly, this one was counted twice. This edge was counted twice for this region and this region. So all the edges are being counted twice as a boundary. Okay, so B is equal to 2e. So boundaries are 2 times the number of edges. Here the total number of boundaries were 12, but edges here are 6. Okay, so the total number of boundaries are always twice the number of edges. Okay, so using this equation in 2, using B equal to 2e in equation number 2, we get 2e is greater than or equal to 3r, which we want to prove. So we have proved the first inequality, 2e greater than or equal to 3r. Now let's prove the second inequality, e less than or equal to 3v minus 6. So from first inequality we have 2e is greater than or equal to 3r. Now we'll just divide both sides with 3. So it will become r less than or equal to 2 by 3e. I will add v both sides. We get r plus v less than or equal to 2 by 3e plus v. We name this as equation 1. Now from Euler's formula we have v plus r, number of vertices, plus number of faces, minus number of edges is equal to 2. I have brought number of edges the other side. So v r is equal to e plus 2. So we'll name this as equation 2. We'll put equation 2 in 1. So we'll get, instead of r plus v, put e plus 2. So we'll put this here. So we get e plus 2 less than or equal to 2 by 3e plus v. Okay. Now this implies we'll multiply by 3 throughout the equation. So 3e plus 6 is less than or equal to 2e plus 3v. Okay. So now 3e plus c is less than or equal to 2e plus 3v. So we'll bring this 2e this side. So it will become e less than or equal to 3v minus 6. So e is less than or equal to 3v minus 6. So that's what we have to prove. So next example, K5 is not planar. I have already explained you this diagrammatically. So mathematically we'll prove that K5 is not planar. Here you can see that number of vertices. How many vertices are there? 1, 2, 3, 4, 5. So there are 5 vertices and 10 edges. Let us assume the contradiction that K5 is planar. So for a planar graph, we have just proved this inequality, that e is less than or equal to 3v minus 6. Okay, so planar graph we have this, e is less than or equal to 3v minus 6. Okay, so let's put number of edges 10 less than or equal to 3 times number of vertices 5 minus 6. Okay, when you will solve this, you will get 10 less than or equal to 9, which is contradiction. 10 is greater than 9, it can't be less than 9. So our assumption, we have assumed that K5 is planar. Our assumption is wrong. K5 is not planar. I hope you have understood this video. If you have any doubt, you can ask me. Thanks for watching this video. Have a good day. Thank you.